Hi, so we're team one. This is our presentation. It's titled Alexa, I don't know who she is. Discourse-driven co-reference resolution. I'm Angela.
I'm Cecilia.
I'm Eduardo.
I'm Phil.
This is Jeshwanth.
So we're going to get started with the motivation and background. And first, we really want to introduce you to Meeting Athena, which is a social bot that was a finalist in the Amazon Alexa Prize competition. It's aimed for an open domain dialogue system so that users can really talk about anything. And this is just a simplified version of our architecture where we have the user utterance going into the ASR module, into our natural language understanding pipeline, and then into the other managers and response generators to actually output a system utterance. And so what we really impacted was the co-reference resolution module, the named entity recognition and named entity linking module, and the discourse model. And so how those three things work together is that if the named entity recognition or the co-ref module actually resolves an entity, those entities will get put into the discourse model. And then our response generators, specifically the flow RG and KG RGs for the topics of movies, music, TV, and sports, would be able to actually know that the user actually mentioned an entity because that information is in the discourse model. Now, if those RGs actually bring up an entity within the system utterance, they also input that information into the discourse model, which can then be used by the co-reference model or the NER/NEL. And in addition to that, our co-reference resolution model, once we actually do resolve the entity, our named entity linking module will actually link that entity back to our database. So it's really a nice flow of information. Next slide. And so you might be wondering, what is co-reference resolution? And so here we have an example where the system says something like, when I'm interested in watching a movie, the actor Melissa McCarthy is one of my favorites. So the system here brings up that entity, Melissa McCarthy. We would assume that would be put into our discourse model. Then the user says, I don't know who she is. And this is where co-reference comes in. So we want to relate she to Melissa McCarthy. So we're really relating these pronouns to the entities itself to then produce a more salient response. So here you can see in the next utterance, this is where we actually see the effect on the system. So without co-reference, we say something like, do you like any of Melissa McCarthy's movies? And it's not really the most salient response, knowing that the user just said they don't know who she is. And so I would want to know also that we're focusing on the pronouns it, they, that, she, he, her, him, and they. Next slide.
So now we're going into our requirements and proposal. So we are creating a open domain dialogue discourse model that tracks which entities are currently in focus in the conversation, whether or not they're realized by a pronoun, whether they're introduced by the user or the system, and retain the entity representation information based off of the Wikidata knowledge graph. Next slide. So for our proposal, we're proposing three different models. First is the role-based model, which is created with our handcrafted roles. The benefits of this model is that it is low latency, which is important because of the amount of traffic that we get through our system daily. It is also easily expandable, which helps with our analysis, and it can fully utilize the discourse model. Next is the neural model, which is a fine-tuned LNLP co-reference model. It can handle more complex cases. It does not require the discourse model. And what this means is that we can use the raw utterances as input, and it is more resilient to the user errors. And finally is our ensemble model, which is a combination of both the role-based and neural model. We hope that this model can perform better by specifically targeting their strengths and improving recall. Next slide. So now going to design. So for our discourse model, the discourse model is basically a function of the entity types and context used. Entity types are labels that the knowledge graph put on the entities. And for our Athena system, we use a subset of them, which are listed below for the four topics of music, TV, sports, and movies. The discourse model does not track the abstract entity types. And context used is the number of conversation turns that we take into consideration. For our experiments, we mainly only use 2 utterances of context. And this is because from our logs, we noticed that only 3% of the examples require further context. Next slide. So now for our rule-based approach, on the left is a sample conversation. And this example also shows our fallback rules, which are rules that relax the constraints based off of analysis of our user logs. So we have Stephen Curry has won 3 NBA championships. What do you think about that? The user says, I don't know who she is. And we detect the pronoun she in the user utterance. So now we look through our rules. First is we check if there are entities present in the discourse model. If there are no entities in the discourse model, then the rule base cannot resolve that pronoun. But in our case, since we do have an entity, Stephen Curry, it has a type, which is the American basketball player. And because it is a person, we also have the gender, and then we have the Wikidata IDs. And because this is a gender pronoun, we do a gender pronoun agreement check. And if there was a female entity in this list as well, it will resolve the pronoun she to the female entity. However, we do not have one, so we go to our fallback case, which relaxes that gender requirement and resolve the entity she to Stephen Curry. This is because we notice from our logs that if the user does not know the entity we are talking about, they oftentimes get the pronouns mixed up, or it can also be an ASR error that mixes up the he and she. So for other types of pronouns, such as it and that, they will have their own rules and fallbacks based off of our analysis. Next slide. So next is the neural model. The neural model is based off of the LNP Coreference module that is fine-tuned on our data set annotated from the live traffic, which we will show in a later slide. However, for inference, the input, we use the concatenation of the last system utterance as well as the current user utterance. And the output is the coreference cluster involving the pronoun in question and the antecedent. Next slide.
Okay, so upon analyzing our fine-tuned Coref model and rule-based model, we found that our fine-tuned Coref model had a much higher precision than a rule-based model. In addition to that, we found the rule-based model had a higher recall. So that motivated us to try a simple ensemble model where we would run our fine-tuned Coref model first on our input. And if we don't get an antecedent for the pronoun detected, we would run a rule-based model. And if we do find an antecedent for the pronoun, we'd use that from the fine-tuned model. And the architecture is shown below. Next slide.
Next slide, please. So this is a data overview of all of our data. So our data can be generally divided into real data and synthetic data. For real data, it's annotated by us. It's from between the system and Alexa users, and we have 7,888 of those. And for synthetic data, we created at least 600 case samples per topic, but not all of the data is used in training, and we have a distribution of our topic and pronoun. Next slide, please. So here's our data pipeline. We first gather our data, like I mentioned before, it's between our system and Amazon Alexa users. And then we do data annotation for co-reference resolution. And then we do quality check. So on the real data side, we would then split our data to have the tenfolds. And on the synthetic data side, we would then do synthetic data generation, and then we would do synthetic data sampling. And then at the end, we would merge our real data with synthetic data, depending on the ratio of how much we want to experiment and how much we're sampling. And then they will be our final train, def, and test set, but synthetic data is only added to train. And then at the last step, we have data format conversion, because we're following column format with like 12 different columns with information and stuff. So next slide, please. This is how we do data annotation. We have to label pronoun and focus, and the gold label for co-reference resolution, which is which name entity is being referred to by the pronoun and focus that labeled earlier. And then for this task, we also introduced reason type. We have 8 different reason types in total. Below, we have an example of 2 of them. And the reason for this is because we want to be able to expand the task for later. There might be like abstract reason type, abstract entities that we would not be resolving for the current task, but it could be helpful for some other tasks in the future. So we have not an entity like in the second example that is referring to 87 tracks. The gold label will still be labeled. Reason type will be not an entity. We will filter by this for our current task. Next slide, please. So this is a slide on how we create our synthetic data. This is like a really general example. So we have the real and the system utterance, that's the system utterance, and we would find the musician, genre, song, like different entities, and we would find the matching templates. And from these templates, we will fill in these templates with the corresponding information from Wikidata. Then we will match filled in templates with user responses matching the templates. So for example, on the right-hand side, we have three user utterances that might be matching to the original template. So we would mix and match them and create more data that way. We would also added the GOAT label to update to be correctly reflecting the current GOAT label, and pronoun and reason types would stay the same throughout this process. Next slide, please. So this is a slide on how we do our data split. We first have our full set of real data. It's 7,888 samples. And then we would set aside 10% for our dev set, and the dev set stays the same throughout this whole process. So we can do error analysis later on the dev set. So for the rest of the 90% of our data, we do a 5-fold, and then we shuffle at step 2 again, then we do another 5-fold, so we end up with 10 folds. So the thing to note is that for experiments where synthetic data is added, it's only added to each split's training data. So after this point in life, so the train that you see in this diagram, we would add synthetic data to those. And then next slide, please.
So for our experiments, starting with the rule-based model, we run 10-fold cross-validation as our first step, and then after that, after we've run the cross-validation, we use the test scores to empirically grab the how well the 10-fold cross-validation did. After that, we analyze the dev set to check the individual cases so that we can further dissect what samples and what cases we get correct and incorrect, to then move on to step 4, which is to improve the model and to improve the rules of the model. We use this we use this experiment cycle as well in the neural models, which we'll see in the next slide. The neural model baseline is trained on the Connell data, and then our fine-tuned is then further fine-tuned on the set of annotated samples described in the last dataset slide. We can see that the system utterance is in blue and the user utterance is in red. And on the right-hand side, you can see it in Connell format, which is the way that we train the train the models. We can see that just lose it is annotated with a 1 in parentheses, and the corresponding pronoun for that entity is also labeled a 1 in the red section. Next slide, we will see the further experiments that we do with the entity list. Here we hypothesize that by adding the entity list via semantic markup, we would increase performance. And so we do various experiments with adding the semantic markup, which is a set of entities in between those 2 separation tokens, and each entity is separated by a pipe character. Here in the bottom, you see that we added it to the back. In the next slide, we'll see the synthetic data sizes in this graph here. You see the different data sets that we've constructed. We do this because we wanted to test a few hypotheses, which is to see if synthetic data being added to the trained data would be beneficial in terms of improving the model performance, and also see if the curating the data specific to tailoring it via the dev samples that we analyze to tailor it to the errors that we see in the dev set. And so in the table, you'll see the sizes of those data sets in comparison to the regular train set that we have of real world examples that we got from the live system.
This is evaluation. Next slide. So to measure the performance of our models, we use standard F1 precision recall. And on the table on the right, we can see what the true positive, false, negative, and true negative cases are in the context of this problem. So for true positive, that's when the model predicts prediction of the model matches with the true label, where there's an actual antecedent and pronoun present. False positive is when the model doesn't predict the right antecedent. True negative is when the model predicts no antecedent correctly. And false negative is when the model predicts no antecedent, but there is one. In addition to that, we compared our predicted antecedents to the gold label with the exact match. In addition to that, we to compare the models' performances across between each other, we use pairwise t-tests to measure the statistical significance of the results to provide further evidence to show that one model is better than the other. For example, we did it between our fine-tuned neural model and our baseline out-of-the-box model. In addition to that, we did push our rule-based model into our live system, and we made live dashboards, which are able to extract from the conversation logs cases of anaphora resolution. And we were also able to divide them based on response generators to see how our model is performing across the entire system. Next slide.
Yeah, so in conclusion, here are our main results. So we are listing here the baseline, which is the out-of-the-box LN NLP model. As we can see, that doesn't do the best. Then we have the rule-based model, then the fine-tuned, and this is only on the training set that was mentioned earlier. We also have another training set where we actually include all entity types. And then we have I'll go more into that later. And then we have our ensemble model, which we already talked about the design, our fine-tuned semantic markup. This is where we actually put that markup in the back that actually performed the best. And then we have our two synthetic datas. The two that were performed the best for those experiments was synthetic 200, just entities plus the training data, and then synthetic curated with just the training data. And if you go into the next slide, we actually rank each of these by performance ranking. So we actually have the first one, which is the fine-tuned trained on all reason types. And so I'm going to now go into our takeaways for each of these and our main conclusions. So the takeaway for the first one, why we actually think that it did the best, is because one, it actually included all entity types, while in the second one, we actually limited the entity types. So if we actually, so we had that example earlier with 87 tracks. If we were to actually process that into colonel format, we wouldn't have labeled that at all when training, but for the first one, we would label that information. So we're kind of suggesting that maybe this means that it's a more adaptable data set for potential abstract entity types. And if the system actually wants to start recognizing more entities, this would actually, this is actually a sign that they would be able to also do that. And so the second one, we're saying that there's too many false positive cases. We're thinking that the not an entity reason types and just them as like null values essentially probably lowered our scores because the model was probably just nothing. Then the synthetic, we are assuming that there was just not enough variation in that data set. For the markup, we're assuming that just too much noise in the input, while with the ensemble model, why we think that actually performed worse was because the rule-based model just had too low of precision in comparison to our fine-tuned model. And then the rule-based, it can't really handle difficult cases like pleonastic it cases, or if there was multiple antecedents present, and that happened a lot in the cases of they or it or that. And then we also have our baseline, which did the worst, and we're assuming that's because the onto notes data set isn't necessarily geared towards dialogue, while the rest of these were very much specific towards our user utterances and what we were working with. Next slide, we're just going to go into the demo now.
Welcome to our demo on Discourse and Coreference for open domain dialogue systems. Created by Phillip, Angela, Jesh, Cecilia, and Eduardo. Hi, this is the Alexa Prize social bot, Athena. It's nice to speak with you again. I hope you're having a good day. How are you doing?
I'm good. Let's talk about music.
I love talking about music. Is there a musician or band you'd like to talk about?
I'm not sure. What about you?
I like to talk about the musician Elton John. Do you like Elton John?
Oh yeah, I really like the song Rocket Man.
Right. Some of my favorite songs from Elton John are from the 1970s. I especially like Crazy Water. Do you like it too?
I have listened to it.
Alexa, let's talk about TV.
Have you seen any television shows that you like recently?
I have been watching Nancy Drew.
Nancy Drew is a great show. Have you seen all of it?
No, not yet. I've only seen part of it.
Alexa, I want to talk about movies.
I love talking about movies. Is there a movie actor or actress that you like?
I love Amy Adams.
Amy Adams is married to Darren Lagallo and has one child.
Yes, I heard she has one daughter.
Anyways, I'm curious. What do you think about this? If you could watch one movie for the rest of your life, what would it be and why?
I would have to say La La Land. That movie has a good story and it makes me so happy to watch.
Alexa, I prefer sports. Let's talk about it.
Let me know about your thoughts. Would you rather be an amazing football player or an amazing baseball player?
Probably football, I guess.
Picking a football player is an awesome choice. I would rather be a baseball player. Is there an athlete you like?
Alex Morgan's cool.
I really like the athlete David Beckham. What's your take on him?
I mean, he's cool and he's really talented.
Let's talk about music.
I love talking about music. What band do you want to discuss?
I want to talk about Justin Bieber.
We can talk about anything you want. Anyways, Justin Bieber has released 61 tracks, which is a pretty good amount. Do you think that's a lot or not?
Did he really?
Do you like the genre, contemporary R&B? Justin Bieber's song Baby is a good example of that genre.
That song is good. I also like Stay.
That's great. Alexa, stop.
Special acknowledgements to Professor Walker, Professor Ratnaparkhi, Liren, Christian, Jaziel, and Venkatesh.
That is the end of our presentation.
Welcome to our
Okay.
demo on Discourse and Coreference for
Okay, thank you, Team 1, for a talk and a demo.